So now we're ready to see where the resting potential comes from.
Let's make this more like a real-life situation, of sorts. Let's imagine the cell as a bar. 2 bars, actually. An inside bar, representing the intracellular space, and an outside bar, representing the extracellular space. There's quite a rogues gallery hanging out in both bars. Some of the patrons are quite mobile, others less so. Going back to our drunken sailor analogy from a minute ago, we'll think about cations, positively charged ions, as male sailors, and anions, negatively charged ions, as female sailors. By default, the gender balance is pretty close to equal. Let's pay attention to 2 groups in particular. This group of male sailors from the US Navy will be our sodium ions, and these guys from the British Navy will be our potassium ions. It's Fleet Week. There are 2 forces that drive the resting potential. First, the sailors from each navy, American and British, are always independently trying to balance themselves out between the 2 rooms, so they have equal coverage in both places. If there somehow got to be more Brits, say on one side, then they'll work to correct the imbalance. This is diffusion. But there's another force at work. They're also trying to balance out the gender ratio on both sides. If, say, there gets to be an excess of male sailors on one side, then they'll feel uncomfortable and try to get to the other side. Female sailors, anions, feel the opposite affinity. This, of course, assumes that the sailors are all heterosexual. Let's not push the analogy too hard, lest it break. This gender balance-seeking force is the electrostatic force. Here's where it gets interesting. The reason that there's a negative resting potential inside the cell is because there's a British bouncer who only lets the Brits go between the 2 rooms.
Hello.
By default, there are a lot of Brits in the inside room, and only a few of them in the outside room. Because of this imbalance, they want to go out. Remember, they want to fulfill their mission to equally cover the 2 territories. The Brits, who are all male in this example, would all rush through and balance out to equal numbers in both rooms if it weren't for the fact that doing so would badly disturb the gender ratio. If they completely balanced out their numbers across the 2 rooms, there would be a significant excess of men in the outside room. You see, the outside room already has a bunch of males, including our friends, the American sailors. In principle, these guys could trade places with the Brits and preserve the gender balance. But here's the key. The British bouncers don't let them move into the inside room. They're stuck. The equilibrium potential is all about balance. It's a balancing point between diffusion and electrostatic forces. In our analogy, it's governed by A, the desire of the Brits to balance out their numbers, B, the uncomfortable feeling that they feel when there are too many male sailors in one room, and C, the relative ease with which each type of sailor can move between the 2 rooms. The British can move easily because of the British bouncer, but none of the other sailors are allowed to pass through. In a nutshell, the equilibrium potential occurs when the electrostatic forces caused by having a charge imbalance exactly balance out the force of diffusion that drives those same ions from where they exist in high concentration to where they exist in low concentration. In our analogy, the resting potential is the exact level of gender imbalance that just balances out the sailors' desire to even out their numbers. We'll explore this concept in greater depth, but this is the most fundamental thing you need to know about equilibrium potentials.
We haven't talked yet about how ions, or sailors, move from the inside of the cell to outside. But don't worry, we'll get to that part soon. In the meantime, let's explore the idea of concentration and electrical gradients in more depth.